could not happen if the electromagnetic interaction is there, because two positive charges, because two positive charges cannot attract each other, they'll repel, right? So deuteron problem, which is consists of the nucleon's energy, binding energy, which is not a gravitational interaction forces, gravitational interaction between the nucleons, which is also not the electromagnetic interaction between the protons, isn't it? Because if the gravitational, if you consider it as a gravitational interaction, the gravitational interaction is much less than the binding energy per nucleons. Whereas if you consider it as an electromagnetic interaction, uh, as a force which is occurring in the nucleons, in the nucleus, that is also not correct, because this electromagnetic interaction occurs only between the, uh, cannot occur in the nucleons, because the interaction between the protons will be repulsive. Due to the repulsive forces, cannot happen. It cannot bind together. It will repel, right? The nuclei may be split. Okay. Thus, we must have a type of force other than above to act between the nucleons within the nucleus. So, electromagnetic interaction is not the electromagnetic interaction which is binding the nucleus, and also not the gravitational interaction which is binding these nucleons. So, what is the force other than these two forces, which is there, which is binding these nucleons within the nucleus? What is that force? Let us see. This force is very strongly attractive up to a certain maximum distance between the nucleons. So this force is very strongly attractive up to a certain maximum distance between the nucleons, which is of the order of 2 femtometers. So 1 femtometer is equals to 10 to the power of minus 15 meters. Very, very much less distance. Force is strongly attractive. So the force is very strongly attractive up to a certain maximum distance between the nucleons. So it is attractive up to a certain distance. Okay, the force is very much attractive up to a distance of 2 femtometers. The distance is known as the range of the force. So, so this distance 2 femtometer is the range of the force between the nucleons. How much distance? Distance is 2 femtometer. 2 femtometer is the range of the force between the nucleons. Beyond that distance, the force is negligibly small. So, up to this 2 femtometers, the attraction between the nucleons is very strong. When the distance increases above than this 2 femtometers, the force is negligibly small. The force decreases very rapidly, isn't it? So, we can say that these forces are short range forces, 2 femtometers. Okay, this is the range of force. Beyond that distance, of course, is negligible. It is known as strong interaction. So these interactions are called strong interaction. The exact nature of this force is not fully understood. So what is the nature of this force? Not actually fully understood. However, some idea of its nature can be inferred from the ground stable properties. There are some, uh, we can find the nature of these forces by some properties of deuteron. Okay, some properties of deuteron, so that we can understand. A deuteron is what? Actually, a deuteron is one proton and one neutron, isn't it? So its mass number is 2 and its number of protons is 1. So the deuteron, the simplest proton neutron bond system, this is the simplest one, which is having one proton, one neutron. Okay? So that if you can study this simplest form of this element, we can correlate with the other nuclei. So we are taking the simplest form to study these interactions actually. So deuteron, the simplest proton neutron bond system we are studying. So what are the properties of deuteron? Let's see. So properties of deuteron. So here The extraordinary stability of alpha particle shows that most stable nuclei are those in which number of protons or neutrons are equal. Okay. So, so alpha particle, if you see the alpha particle, it has extraordinary stability. Why? Because it contains a neutron and a proton, isn't it? So, so number of protons, sorry, it contains two protons and two neutrons. As this contains two protons and two neutrons, the number of protons and number of neutrons are equal. Hence, this alpha particle is it has extraordinary stability, isn't it? In the same way, the deuteron is also having number of protons and number of neutrons are equal. So the deuteron consists of two particles of roughly equal masses, capital M. So so these two particles, neutron consists two particles which are having same nearly equal masses. So the reduced mass of the system, we will take the reduced mass of the system, that is small m capital M by m plus 1. Otherwise, we can consider it as half m because uh, there are two particles, right? So we are taking half m as uh, reduced mass of the system because it is a two body problem which are having nearly equal masses. So we are considering this as half m. So this is the first property of this deuteron. So if you go for the second property, the binding energy of deuteron is very small. So the binding energy of deuteron is small. Its experimental value is 2.2 mega electron volts. Since milli electron volts. Since the energy needed to pull a nucleon out of a medium mass nucleus is about 10 eV, we must regard the deuteron as loosely bound. So, so the binding energy of the deuteron is small. Its experimental value is how much? Is 2.2 MeV, isn't it? But to pull out the nucleon out of that nucleus, we need how much energy? 8 MeV, isn't it? So actually we need 8 MeV to pull out the nucleon, but the deuteron will have only 2.2 MeV of energy. Actually, experimentally it has small energy. So we must regard deuteron is, so that's why we can consider that deuteron is loosely bound. Okay. The angular momentum quantum number, the angular momentum quantum number, often called nuclear spin. So we'll call it as a nuclear spin, angular momentum quantum number. We'll call it as a nuclear spin of the ground state of a deuteron determined by number of optical, radio frequency, and microwave methods is one. It suggests that spins are parallel state and orbital angular momentum of the deuteron about their common center of mass is zero. So the orbital angular momentum to deuteron about their common center of mass will be how much? It will be zero. Thus the ground state is taken as 3s state. How much? 3s state we will take. Okay. So the angular momentum quantum number we will call it as a nuclear spin, the ground state of the deuteron. So how it was determined by number of optical radio frequency microwave methods. Okay, any one of these methods, optical or radio frequency or microwave methods as well. So when the spins are parallel, in the orbital angular momentum of deuteron about the common center of mass is zero. Okay. The ground state is 3s state. The parity of deuteron as measured. Now we go for the parity. Parity of deuteron are measured indirectly by study of nuclear disintegrations and reactions for which certain rules of parity changes exist. Is even. The parity of deuteron as measured indirectly by studies of nuclear disintegration and reactions for which certain rules of parity change exist. Is even. So deuteron parity will be even. The sum of magnetic dipole moments of a proton that is 2.79 muon, and neutron minus 1.79 muon, 1.9 muon does not exactly equal to magnetic moment of electron. So if you go for the magnetic dipole moment of a proton, the proton dipole moment will be 2.79 muon, and for neutron, the uh, magnetic dipole moment will be minus 1.9 muon, which is not equals to deuteron actually. These sum of these two, because proton and neutron combined we called as a nucleon, and deuteron will have proton and neutron. Right? So if you see the magnetic dipole moment of this proton and neutron individually different to this one. So not exactly equal to the magnetic moment of deuteron. So that is 0.858740 muon measured by magnetic resonance absorption method. Okay. The radio frequency molecular beam, the radio frequency molecular beam method has been employed to determine the quadrupole moment of the deuteron. So how we use the radio frequency molecular beam method to study the quadrupole momentum of this deuteron. Okay. Which method we are using? We are using the method radio frequency molecular beam method. So by using this method, we found that the quadrupole moment of the deuteron is 2 is equals to plus 0.0028 into 10 power minus 28 centimeters. In the earlier class only, we have said that when the quadrupole moment is positive, the shape will be how much? The shape will be prolate spheroid, isn't it? When the Q is positive, the shape of the nuclei will be how much? How it will be? Prolate spheroid. When it is negative, it will be oblate spheroid or X-shaped spheroid. We say, and if the quadrupole movement is zero, then it will be spherical shape. Isn't it? So as this is plus quadrupole movement is positive, this will be in sorry, prolate spheroid in shape. So the quadrupole momentum of the deuteron will be plus 0.0285 into 10 power 8 centimeter square. Okay. This shows the departure from the spherical symmetry to charge distribution. So the departure of the spherical symmetry by for this Q value. The positive sign indicates that this distribution is prolate rather than oblate. As this is positive sign, the Q value is positive sign, the Q value is positive sign, which indicates that this is in a prolate spheroid in shape. Okay. The electric dipole and quadrupole moment and magnetic moment discrepancies can be explained if the ground state is a mixture of flip state, 3s1 and 3d1 having even parity. If these are having even parity, these states are having even parity, then we can explain this quadrupole and magnetic moments. Okay. The percentage probability of finding deuteron in this state is, what is the probability of finding the deuteron in this state? It is 4 plus or minus 2%. Okay. 4 plus or minus 2%. As deuteron spends most of the time in spherically symmetric state. So as this deuteron spends more time in the spherically symmetric state, that's why this state is having this value. Since the neutron has no charge, as the neutron has no charge, the force between the neutron, sorry, between the neutron and proton cannot be electrical. So if the sorry, if the neutron, as we are considering neutron as we know that neutron is having no charge, is there any attraction or repulsion occurs between them? No, isn't it? So if there is a proton and a proton, there may be an attraction force between them or repulsive force between them. So if there is proton and proton, there will be repulsive force only. If there is electron and a proton, there may be an equivalent attractive force will be there, right? As it is one electron is a negative and a proton is a positive charge, positively charged, isn't it? But a neutron doesn't have any charge. Means if you consider a proton and a neutron also, there will not be any charge because will not be any attraction or repulsion forces because the neutron is neutrally charged and the proton is positively charged. If uh, if the neutron has any charge rather than a neutral charge, it may attract or repel, but it doesn't have any charge. That's why this will not be in a force of attraction or repulsion. Cannot be an electrical force. This force cannot be magnetic as magnetic moments are very small. As these magnetic, this cannot be magnetic also because these magnetic moments are very small. It cannot be gravitational force. Cannot be a gravitational force between those things because as the masses are very small between proton and neutron. So we must accept the nuclear force as a new type of force. Hence, these forces are not electrically attractive or repulsive, and these are not gravitational force because these are very less masses, which are having less masses, and these do not have much magnetic moments, so that we cannot consider it as a magnetic forces. So we must accept that is a this type of forces are new type of forces which are short range forces. So we must accept nuclear force as a new type of forces. We must accept this new type of forces as a nuclear force and which are short range forces, attractive in nature, and along the line joining two particles. Okay, along attractive in nature and along the line joining two particles. That is central. Since a central force cannot account for the quadrupole moment of a neutron. Since central force cannot account for the quadrupole moment of a neutron. The force depends only on the separation of the neutrons. So these nuclear forces depends only on separation of nucleons. How much the distance between those neutrons, it depends, okay? Not on the relative velocity or orientation of neutron spins with respect to the line. So it doesn't depend on the nucleon spins. The force doesn't depend on the nucleon spins. Sorry, relative velocity. So the force depends only on separation of the nucleons. Okay, this force can be derived from a potential. How it can be derived? It can be derived from a potential. Since the force is attractive, as this is force, as the force is attractive, we can derive from the potential. Okay, that is V of R we are considering. V of R is a negative and decrease with decreasing R. So V of R is what? The potential which is negative versus with decreasing R. Since it is short range. Okay. V of R vanishes for V greater than B. Sorry, R greater than B, where B is nearly 3 Fermi. If the R value is because these forces will be up to only 2 Fermi, right? So if the value is nearly B 3 Fermi, then these forces will be then this potential will vanish. Okay. So these are the properties of deuteron. As we know, what is deuteron? Deuteron is a element which consists of only one electron, one proton, and one neutron, which is the simplest one to solve the problem of this binding energy, the binding energy between the neutrons, and to study the forces between nucleons in the nucleus. Okay. So by studying the simplest form of this deuteron, we can understand the heavier nucleons also. Nucleus also. Okay. Hence, we are solving this deuteron problem. Okay. This is the basic one. So we have seen the properties of deuteron. Uh, and we have seen that parity is even for these deuteron, and the sum of the magnetic dipole moments are different from the individual proton and neutron to the deuteron, isn't it? So, and also there will be the deuteron shape will be a prolate spheroid shape, and the positive sign because that we have seen. The next one is ground state of deuteron. So we will see the ground state of deuteron. The Schrodinger equation for a two-body problem. Two-body problem for the two-body problem, the Schrodinger equation will be how much? This one, del square psi plus 2m by h cross square e minus v by v into psi is equals to 0. Here E is the energy, V is the potential, and psi is the wave function. Del square is a Laplace. So this is the equation we have. So M is what here? M is a reduced mass we are considering, and E is the energy of the system equal to the binding energy of the neutron. So energy of the system which is equals to binding energy of the neutron. V is the potential energy. V is what? V is the potential energy described the forces acting between the bodies. Okay. V is the potential energy describing the forces acting between bodies. This Schrodinger equation for free S state, that is I is equals to 0, the deuteron is how it will be this one. Here if you see, we have, I hope you know what is del square. Del square here it is deuteron is in a spherical shape. In a three-dimensional space, we are considering this as r theta phi coordinates, spherical coordinates we will consider. Here theta phi we are neglecting and we are only considering the radial part. We are taking the radial part only. That is del square is equals to, we can write 1 by r square d by dr r square and dou psi by dou r, isn't it? Plus 1 by r square sin theta d by d theta sin theta d. I hope you know that. So how it will be actually del square only. So in the spherical problems, we will consider three dimensional of r sin theta, and uh, r phi. R theta and phi terms we will take. So here in this case, we are considering only a radial term, which is 1 by r square. In the place of del square, we are considering 1 by r square d by dr r square d by dr, isn't it? So this is how we have written this. So 2m by h cross square e minus v of r in psi of r is common here. So the Schrodinger equation for three states of deuteron is given as this one. In this case, the reduced mass m is equals to, as we know, this is a two-body problem. We can write the reduced mass m is equals to 1 by 2 capital M, isn't it? 1 by 2 capital M. That where capital M is what? Mass of the nucleon. So mass of the proton and neutron is given by nuclear. We expect the ground state to be spherically symmetric. That is just it. Okay. So we are considering that ground state will be spherically symmetrical. Okay. So that psi of r depends only on small r. So psi of r will depend only on smaller, that is central modified force. Central modified force. Substituting psi of r is equals to u of r by r. U of r is radial wave equation. So in the place of psi of r, we will substitute u of r by r. Okay. If you substitute u of r by r and you replace in that above equation, you will get the equation as this. So that will be d square u by dr square plus, here small m is equals to 1 by 2 capital M, right? So capital M by H cross square, if you substitute this value, this half M is equals to plus 1 by 2M, and u psi of R is equals to P of R by R. In the above equation, that is equation 2, you will get this equation, that is d square u by dr square plus m by capital M by H cross square v minus v of R into v is equals to 0. So I hope you understood this one. The wave function of a bound state of neutron is not known here, depended on the exact shape of potential v of R between the proton and neutron, provided the potential of short range is chosen. The wave function of the bound state of neutron is markedly dependent on the exact shape of potential. So this wave function bound state of neutron is not dependent on the shape of the potential between the proton and neutron, provided potential of short range is chosen. Okay. For the ground state of total energy E is negative. So the ground state of neutron, the the energy will be negative. The energy is taken as negative and is equals to minus P. Okay. How the energy is? It is negative and it is taken as minus P. So the B is the binding energy of the neutron. What is the B here? B is the binding energy of the neutron. Thus, equation 3 can be written as how? The equation 3 can be taken as like this. D square u by dr square plus m by h cross square, m by h cross square, v naught minus b into u is equals to 0. Here, energy capital E is be taken as minus b. Okay. So take that minus b and you will get this equation. And this equation, the value of this one will be d square u by dr square plus m by h cross square v naught minus b to u is equals to 0. And here r will be less than b. Okay. R will be less than d square. If you rearrange the terms and if you take the potential v is v naught is equals to 0, and you can write this equation, because when r is very much greater than, sorry, r r is greater than b, what happens? There is no attraction or repulsion between those neutrons. The forces will be reduced and the potential is taken as 0. Okay. When r is greater than b, potential will become 0 here. When r is less than b, it has some potential, that is v naught. Okay. That is d square u by dr square plus m by h cross square into minus b to u is equals to 0 for r greater than b. This is the equation 5. This equation can be written as, so the equation can be written as d square u by dr square plus k square u is equals to 0, or d square u by dr square alpha square u is equals to 0. This is how we will write this equation. So when r is less than b, this is how we can write. This is d square u by dr square plus k square u is equals to 0, and we can solve this equation and we can find the value. Okay. So here m by h cross square v naught minus b is taken as k square. Okay. In the same manner, we will take this one also. This is d square u by dr square alpha square u is equals to 0, where alpha square is equals to m by h cross square minus b. So this is how we will take, that is d square u by dr square plus alpha square u is equals to 0, where r is greater than b, greater than b. So here k square is how much? Just now we have seen from k square is m by h cross square v naught minus b, where alpha square is how much? M by h cross square minus b, isn't it? So we are replacing, we are writing here where k square is equals to m into v naught minus b by h cross square, and alpha square is equals to mb by h cross square. So we take this equation as 7 and above equation as 6, and we will try to solve the solution. If you solve the solution, you will get the solution as U is equals to, for the sixth equation you will write this solution, that is U is equals to A1 sin kr plus B1 for r less than B. U is equals to A2 sin e raised to alpha r plus B2 e raised to minus alpha for r greater than. So the boundary conditions are at r is u of r tends to 0. R is tending to 0, then it will be 0. Okay? So R is tending to 0, potential will be 0. To keep wave function psi finite. So if R is if R is at infinite distance also, it will be 0. You must not diverge faster than as infinite. Okay. To satisfy the conditions at 0, infinity, 0 and infinity, the solutions are reduced. So to satisfy these conditions, uh, the solutions of 8 and 9 will become like this. U is equals to A1 sin kr for r less than b, and U is equals to A2 e to the power of, sorry, here this will become 0, and here U is equals to B2 into minus alpha. Okay. Because exponentially increasing the r will will take it to 0, isn't it? Exponentially increasing of r will tend to infinity, and which is equals to 0. That's why U is equals to b2 e raised to b2 raised to minus alpha minus alpha. We can get the values of constants a and b, b1 and a1 and b2. We can find these values of a1 and b2. If you find the values of these values will be 1 by 2 pi alpha by alpha b plus 1 whole to the power of 1 by 2. And b2 will be having the value a1 sin kb e alpha b, which is equals to alpha by 2 pi alpha b plus 1 whole power 1 by 2 b by 3. These are the values of a1 and b2 values. Okay, these are the two constant values which are having these terms, that is 1 by 2 pi alpha plus alpha b plus 1 a1 sin kb plus kb into e raised to alpha b is equals to alpha by 2 pi alpha b plus 1 whole power 1 by 2 e. Okay. These are the two values, constant values of this one. On substituting these, the values of alpha 0.32 femtometer, and b is equals to 1.93 femtometer in the above equations. If you substitute the alphas in these equations, you will get the A1 value as 0.16, B2 value as 0.247. Okay. So A1 value you will get 0.16 and B2 value you will get 0.247. With this value, it was inferred that nucleons in the deuteron spend only one third of time within the range of nuclear forces, and thus deuteron is loosely bound. So with these values, A1 values, if you see B2 values, with these values, you can say that nucleons in the deuteron spend only one third of the time in the range of the nuclear force. So it spends only one third of the time in the range of the nuclear force, and thus deuteron is loosely bound. So you can say that deuteron is loosely bound. So this is about the deuteron. To summarize the deuteron, so ground state of deuteron is a two-body problem because one proton and one neutron. So we are considering the Schrodinger equation, that is y square psi plus 2m by h cross square minus y v into psi is equals to 0. And we are writing this is a, as this is a deuteron is a spherical symmetric body. So as we are considering spherical body, this coordinate system will be r theta phi coordinate system. In that, del square can be written as 1 by r square d by dr r square d psi by dr. And other terms, theta and phi terms will also be there, but we won't consider. But we will only consider the radial part and we are writing. In the hydrogen atom also, we write that only radial part, right? So, so we are taking the radial part and we are trying to solve. And we solve the problem by writing these terms, m by h terms. We have take, as it is a two body problem, we will take the reduced mass. So it is equals to 1 by 2m. And also, we'll take psi of r is equals to u of r by r. That is potential u, potential equal u of r. Radial wave function is u of r. And we try to rewrite that equations, and we have written the equations when is r is less than b and when r is greater than b. When r is greater than b, it is beyond the range of the potential. As the potential is zero, we can write this equation as a potential in the nucleus. Within the nucleus, it happens. It is a equation you will get, and we try to solve that equations by these equations, and we will get the a1 and a2 values. Chat by seeing these a1 and a2 values, we can say this is the ground state of deuteron. Now we are going to see the excited state of deuteron. Okay, let us see the excited state of deuteron. So first we will write the radial. First we will write the radial part of Schrodinger equation for any angular momentum left. So just now we have seen in the deuteron also we are written only radial part of the Schrodinger equation. So here also we will write the Schrodinger equation radial part, but we will take the angular momentum term. Angular momentum term, that is L into L plus 1 term into the other. So we will take that term so that we can solve this. So here if you see, that is d square u1 of r dr square. This is the this is the wave function, radial wave function we have just now we have considered in the deuteron problem. So d square by u1 of r dr square plus k square minus L into L plus 1 of r by r. That is angular momentum term, that is L into L plus 1 by r we are taking. So for what is the equation? This is the equation for r very less than or equals to b. Okay, when r is less than or equals to b, this is the equation. When r is greater than or equals to b, then the equation will become alpha square. We will take it in terms of alpha square. That is d square. So that is d square u1 of r dr square plus u alpha square minus L into L plus 1 divided by r for r greater than or equals to b. These are the two cases. But k square and alpha square are having their usual values. In the earlier deuteron problem only, we have considered the k square and alpha square terms and values, right? So if you substitute also, you can get the same equations again. But if you see the general solution of equation 14, if you consider, so we'll take the general solution of this equation 14. This equation involves Bessel's spherical Bessel function. So this involves spherical Bessel functions, that is J of L, and spherical Newman function N of L. So it contains, this general solution contains J of L spherical Bessel function and Newman function, that is N of L. As N of L approaches minus infinity, as R tends to 0, as N of L approaches minus infinity as R tends to 0. So N of L uh, will be taken as minus infinity when r is tending to 0. Okay. Thus, the solution of equation 14 is. So, we can take the solution of this equation as u of u1 is equals to ajl of ar. That is only will consisting Bessel's function. That is u1 is equals to ajl k of r. Here, jl of kr is equals to 5 by 2 pi by 2 kr whole power 1 by 2 jl plus 1 by 2 k of r, where jl of half being the function of half order. Okay. The solution of equation of 15. Now we will take the solution of this equation 15. Now, the solution of equation 15 outside the range of Newton force. So the solution for that one will be consisting two, that is spherical Bessel function and Newman spherical function, that is JL of R and KL of R. That is U1 U1 of R. That is the solution for the 15th equation is taken as 15th equation is taken as U1 of R is equals to D of JL of I alpha R plus IN INL of I alpha R. This is the solution for R greater than B. Okay, R greater than B, this is the equation. Using the boundary conditions at the when the function and its first derivatives are continuous at the edge of the well. Okay, we see the boundary conditions, the first derivatives. Okay, for B less than 1.42 into 10 power minus 15 meters, alpha B is less than 1. Since alpha is very much less than 2, the expression is very small and nearly 0. Thus, we can write JL minus 1 of KD is equals to 0. So, JL of KD can be written as 0. This condition holds for angular momentum except L equals to 0. So, this is the condition where this will hold and for L equals to 0. Thus, the minimum well depth. So for the minimum well depth will be how much? How much it should be? V naught is equals to pi square h cross square mb square. Pi square h cross square mb square is the minimum well depth. Okay, well depth. If you choose d is equals to 2 into 10 power 15 meters. So d equals to 2 into 10 power 15 meters if you choose, and you get V naught is equals to how much? V naught potential value will become 144 MeV, okay, which is almost 4 times as larger as the actual well depth in the ground state. So this will be more than the ground state, okay? Ground state well depth. This potential is very much large comparatively to the ground state, which is 4 times to the ground state well depth, okay? Repeating this procedure for larger and larger values of L, we find the deeper well depth is required to produce a bound state. Thus, we conclude that no bound state exists for L greater than 0 for deuterons. So, if you consider L greater than 0, then there will be no bound states found for the deuterons. As because as it is going to the excited state or larger values of L, the potential well depth will be increasing, right? As the potential well depth is increasing, so we can say that no bound state will exist after L is greater than 0 for Newton. So as the excited state increases, excited state comes, the V naught value, the potential depth will increase. Increase in potential depth. Increase in potential depth means what? There will be much energy needed to come out of that nucleus. Experimentally determined properties. Deuteron is only two nucleon bound system made up of proton and neutron, as we know. So deuteron is only two nucleon bound system, one proton, one neutron. The two other possible So deuteron is the only two-body problem. We have we thought that, but there are other two-body problems will be there. That is two nucleon system, two diproton, that is two helium, and a dineutron do exist. Okay, do not exist in the bond system shell. So these do not exist as a bond system. These diproton and dineutron. The following are experimentally determined properties of the ground state. Let us see the experimentally determined properties of this ground state of deuteron. The binding energy is very small. Here, the binding energy for the deuteron is small. Okay. How much the binding energy? The binding energy of the deuteron is the binding energy of the deuteron is 2.2245 plus or minus 0.002 MeV. Okay, this is the binding energy of the deuteron. The binding energy per neutron in the deuteron is 1.11228 MeV. Whereas the average binding energy is how much? Per neutron is 8 MeV, right? Thus, this is much smaller than the mean value of the binding fraction, isn't it? This is much smaller, right? This is 1.1 means very small comparatively with the mean value of the binding fraction for the nucleon. The mass numbers of 4 or more. Even for alpha particle with A is equals to 4, FB is equals to 7.07 MeV. For helium atom also, alpha particle means helium atom, right? For the helium atom, we have the binding fraction is 7.07 MeV. But for a deuteron, which is having one proton and one neutron, it is having only 1.1122 MeV. For two protons and two neutrons, it is having 7.07 MeV. Thus, it is clear that the deuteron is rather weakly bound structure compared to the most of the nucleon. So we can say the deuteron is very weakly bound comparatively with other nuclei. Okay. The spin of the deuteron, total angular momentum, the ground state in the unit of h cross. So the total angular momentum of the ground state is a unit of h cross. Is JD is equals to 1 and mu d is equals to 0. That is the angular momentum of the ground state, that is deuteron. 0.857414 plus or minus 0.00001. So this is the spin of the deuteron and angular momentum. Okay. The deuteron also possesses a small but finite electric quadrupole moment, which has the value. So it has some quadrupole moment, which is of oblate shape. Its QD is equals to plus 0.8282 into 10 power minus 31 meters. Okay. The parity of the deuteron ground state is even. What is the parity of the deuteron? It is ground state is even. The parity of the deuteron ground state is even. The observed values of the ground state spin and magnetic moment of deuteron give important information about the nature of the state. So the values of the ground state spin and magnetic momentum of deuteron gives the important information about this nature of the state. Okay? The deuteron is made up of a proton and a neutron, both of which are spin-off particles. Proton is a spin-off particle and a neutron is a spin-off particle, having the intrinsic magnetic moments. How the magnetic moments are? Intrinsic magnetic moments. Its magnetic moment is proton magnetic moment is plus 2.7927 and magnetic moment of neutron is minus 1.9131 nuclear magnetons. Okay, it is nuclear magnetons which is having the magnetic moments proton and neutron. Their sum is 0.8796 nuclear magnetons. This value differs only slightly from mu d, that is deuteron, given above. So differs difference in uh, magnetic moments of proton, magnetic moment of neutron minus magnetic moment of deuteron is this means. The difference in the value is very less. Comparatively, the nucleons in the deuteron, that is proton and neutron, if you take the individual proton and neutron magnetic moments, that is magnetic moment of proton, magnetic moment of the neutron, if you add these terms and if you take their sum, this is the sum. But if you take the value of d, this is the value of d actually, mu d, deuteron magnetic moment. So if you see the difference is very small, that is 0.024 to mu, that is magnetic uh, nuclear magnetons. So if we ignore this difference to a first approximation, then we may accept the proton and neutron magnetic moment is aligned anti-parallel in this direction, in the direction. So if you ignore this difference of magnetic moment, that is 0.022 nuclear magnetons, then we can say that the neutron magnetic moment is aligned anti-parallel to the neutron. You can consider that is anti-parallel to the neutron. Since mu1 is negative, since the magnetic moment of neutron is negative, the neutron magnetic moment is aligned anti-parallel to its intrinsic spin SL. So the neutron magnetic moment is how it is aligned anti-parallel to the intrinsic spin. Hence the proton and neutron spins sp and sn must be aligned parallel. How the proton and neutron spins must be aligned? Must be aligned parallel to each other in the deuteron. The total intrinsic spin of the deuteron is Fz is equals to sp plus sn. That is deuteron spin is equals to spin of the proton, spin of the neutron, which is equals to 1, because all these two, this is the spin of particle, this is the spin of particle. Consider the spin of particles and add it will be 1, right? So the approximation in which the difference magnetic moment of proton, magnetic moment of neutron, magnetic moment of minus magnetic moment of deuteron can be neglected. So it can be neglected only when n is equals to 0 is admissible. So when you take n equals to 0, n equals to 0, then only you can consider the approximation of this difference is neglected. So the other two values, L equals to 1 and L equals to 2, will contribute significantly to the magnetic moment due to the orbital rotation. So this L equals to 1 and 2 will contribute to the rotation of this proton, okay, which would introduce considerable difference between these some of these proton magnetic moments and individual neutron magnetic. So next we are going to discuss about the quadrupole moment of a neutron. Let us dive into this topic. Quadrupole moment of neutron. We have seen that quadrupole moment is positive for the neutron, isn't it? The quadrupole moment is positive for the neutron. Due to the positive quadrupole moment, it contains a shape of a prolate spheroid, isn't it? It contains a prolate spheroid shape. Another property which is highly important in connection with the shape of the nucleus is electric quadrupole moment. So this electric quadrupole moment, what it shows the shape of the nucleus, isn't it? This quantity, which cannot be discussed in a simple way, is a measure of deviation of a nucleus from spherical symmetry. So this quantity, actually quadrupole moment, shows the deviation in the spherical symmetry. How much is deviated from the spherical shape actually? If the Q is positive, uh, positive, then what happens? It will be like in a prolate shape, where it is in a negative, then it will be an oblate shape. Okay. So measure of deviation of a nucleus from spherical symmetry. Its magnitude depends on the size of the nucleus. Quadrupole moment magnitude will depends on the size of the nucleus. Okay. The extent of deviation from spherical symmetry and magnitude of the charge. The sign may be positive or negative. The sign may be positive or negative. When evaluating the quadrupole moment of deuteron, only the proton contributes to the quadrupole moment. So when you will evaluate this quadrupole moment, of a deuteron, just proton contributes to this quadrupole moment. There will be no contribution of neutron to the quadrupole moment. Okay? Proton will contribute. Okay. So quadrupole moment of neutron only the proton contributes to the quadrupole moment and its distance from the center of gravity. So and its distance from the center of gravity is half the proton neutron separation. So, how the distance is from the center of gravity? It is half of the proton neutron separation. Okay. Hence the quadrupole moment operator for the deuteron is quadrupole moment operator for the deuteron is how much? Q is equals to 1 by 4 3z square minus r square. So the quadrupole moment operator for the deuteron is how much? Q is equals to 1 by 4 3z square minus r square is the okay. This is equals to 1 by 4 z square is how much? In a spherical polar coordinates, z value is taken as r cos theta, isn't it? It is taken as r cos theta. So we can write z as r cos theta. Z square is equal to r square cos square theta minus r square. R square is a radial term, right? Radius it is. So to take r common in this term, what happens? This will be r square by 4. It is 3 cos square theta minus 1. Then write this as 3 cos square theta minus 1. I hope you know that z is what? Z is a spherical polar coordinate element which is z is equals to r cos theta. You can write it as r cos theta. That's why we have written z square in place of z square. We have written x plus cos square theta and it's r square. So this is the value we got. The quadrupole is estimated from the 8 waves behind beyond the potential. The expectation value of the operator is given by. So the expectation value of this operator Q is given as this. Okay. So the S state is spherically symmetric. We cannot have quadrupole moment. So the S state is spherically symmetrical and cannot have quadrupole moment. The first term is 0. The second term is a pure D state term and is smaller than the first. Psi D is equals psi D comma Q psi. That is wave function of a deuteron Q into wave function of a deuteron. That is equals to minus 120 0 to infinity r square omega square of r. Yeah. So 2 into, if you take out 2 to the other side, we can write it as 2 into phi d psi d, sorry, psi d q psi d is equals to root 2 by 10 0 to infinity r square u of r omega r dr. Substituting in equation 2. To substitute in this equation of expectation value of this operator, then you will get the value as like this. Q is equals to under root 2 by 10 0 to infinity r square u of r omega of r dr minus 1.20 0 to infinity r square omega square of r dr. The ground state of deuteron is predominant in the state. The first term predominates over the second. The first state will predominate on second. Okay. Therefore, the effective value of Q for the deuteron is given by. So effective value of this Q is given as root 2 by 10. Only we take the first term. We could consider second term because first term is predominating. R square U of R omega of R d. U of R is a deuteron ground state. Yes, S wave function. So S wave function of deuteron ground state is how much? U of R is equals to ns e raised to minus alpha r, isn't it? Ns e raised to minus alpha r. So this is how the quadrupole moment values will be there. So we have uh, We have meson theory also of nuclear force will be there. So we will discuss in the next class of this meson theory of nuclear forces, how the nuclear forces will be there between how the nuclear forces are attracted, and that will be discussed in the next class. Thank you for participating.